I've got this roller coaster. All right. Shh. And I have point A. I'm going to label a couple points. Point A and point B. And even though my drawing doesn't show it, right? It's a circle that has a radius of r. My loop-to-loop has a circle that has a radius of r.
Is B higher than the
No, it's just the way I drew it.
So
Not the scale.
not scale.
It very well may be. So, here's what we've got. And now I want to know, right, my question is, what does h have to be so that when we get to point B, we're able to get around? Okay? So what height do I need to start my roller coaster at if I'm going to be able to get to point B and make it around the whole loop? Does that make sense? Okay? So what I need to know first is how fast do I need to be at this point? Right? How fast do I need to be here? Now we've done this before already. We've solved for this speed a few times. Right? But we'll go through really quick and do it again. So we know that F, right, equals ma, right? Or the net force is equal to ma. When we're at B and we want to know what is the minimum, the minimum speed, then we remember that the normal force is equal to 0 here. So all we're left with is mg, and that is equal to, oops, I'm way off on this. No, I'm right. Yeah. So then we have v squared over r. Okay? It's because, remember, this is our centripetal acceleration. All right, because we're in that circle. So the m's cancel out, and we get that v squared is equal to gr. Okay? I switched the what? I have it. Sorry. Dave?
I forget. Why is the normal force 0 at B?
Because that's the minimum. That's where we're going to, that's the smallest the normal force can be. If it's larger, it's going to try and push us out.
Oh, okay.
Okay? Yes. Because the track is above us, it can only push us down. Okay? So, and then we know then that v is equal to the square root of gr. So this is the minimum speed with which we have to travel. If we have a normal force, we have to go faster. Okay?
So, like, no matter what the mass is, you have to travel.
No matter what the mass is, because the masses cancel out, so mass does not come into consideration. Okay? All right, so here's what we've got. We now know that's how fast we have to go when we're at point B, and so we don't fall out. All right? So here's what I'm going to do. I'm sorry I got rid of the picture. So I'm going to go with my law of conservation of energy, which says that the initial energy has to equal the final energy. Makes sense, right? Simple enough? Yeah? Okay. All right, so looking at this, then I know that mg8, actually before I even go there, the initial level 1 mode, the initial potential plus the initial kinetic has to equal the final potential plus the final kinetic. All right? So this is when we're at H. This is when we are at point B. All right? So this is when we're at H. This is when we're at B. Okay? Those are our initials and finals. So we know that we've got mgh is going to be our potential. Now we're starting from rest. Right? So we get to the top of the hill, we're going to stop for a second, and then we come down. So our initial kinetic is 0.
Where's the MGH?
The equation for potential is just mgh. Okay? Because we're not moving. We're starting at rest. Okay? Next we have, we'll just call it h because that's what the height is. Next we have mg. Now the height of point B, if we look at our circle, if it's a radius of r, then the height from the ground is equal to 2r. Okay? then we have 1/2 m. Now we know what v is, but we also know what v squared is. V squared is gr. So I'm just going to plug in gr right here. It's capital R. Yes, it should be. Sorry. All right. Are we good with the substitutions I made? Someone?
Why isn't it like the circumference of the circle? Because that's like where the thing would be traveling at.
Because we just want the height from gravitational. It only has to do with how high we are off of the ground. So in this case, it's just the diameter. Okay. So if we're looking at our terms, we see that each term has a mass, so they can go away. Okay. Each term also has a g, so they go away. So we're left with h is equal to, we've got a 2r and a 1/2 r, so that means 5/2 r. Or 2.5 r, right. If that makes you feel better, 2.5 r. In this case, it could go either way. So, if you're a roller coaster designer, that's your ambition in life, is to design roller coasters. One thing that you need to keep in mind is the law of conservation of energy, and the fact that if I'm going to have a loop-de-loop in there, I need to have my starting hill, or I need to have a hill that is equal to 2.5 times the radius of my loop-de-loop. So that's how high I need to start. Now, we may have been able to do this with kinematics and circular motion, but it would have been a lot harder and a lot longer. Conservation of energy, essentially we did it in 2 lines. Right? So conservation of energy, again, is very, very powerful. Okay?